Oh, it's exciting to be here, all the way from New Zealand, the country where lots of agricultural technology takes place. And I lead a team of engineers who build all the software for lots of technology equipment for farms. This is one example here. It's a cattle weighing scale, but it does a lot more than that. It's the database that farmers use while they're handling their animals on farm. It connects to and okay, that's not working. Turn it on, it will. It connects to a lot of devices, and it's a complicated thing, but it tells a story about software architecture. It has a lifetime in the market of about 15 years, and it's maintained for all of that time. And then when it gets replaced, it gets new hardware, but the software is heavily modified again for the new hardware. So it comes about that this device is running some code that I wrote 32 years ago. So these are the quality attributes that I would like to focus on. And ever since I was a very young engineer, I had this belief that if you could write some software, a hypothetical software, that not just met these quality attributes, but optimized them, got them completely optimal, then it would have a certain structure. And I wanted to know what the structure might be, because it would be a really good shortcut. It would tell me how to organize my code. The alternative is this. It takes a long time to master all of these things, I have found. And even if you do master them all, it's a lot of stuff to juggle to solution for these quality attributes. So I was even more motivated to find a template architecture that would just tell me straight away, how do you organize code to get these quality requirements? I searched and searched, and I went through most of my career without ever finding it, without ever knowing what this architecture should be. But finally, after 40 years of making mistakes, making messes, I finally have it. The turning point was when I was reflecting over some of the code that we had written, and there were two pieces of code that had not degraded, unlike all the other code. It was like being in a rubbish dump and you see two shiny pieces of metal that hadn't gone rusty. And you're thinking, oh, that's weird. Why haven't those gone rusty? There's something going on here. They'd been under maintenance for a long time. They did complicated things, but they started simple and they'd stayed simple. And it wasn't what they did that made the difference, because each of them did exactly the same job as some much older software that I'd written long ago, and was a complete mess, a big ball of mud, and maintenance had come to a halt. So it wasn't what they did, it was something about the way they were written. And this is what it was. The top one was how all our other code had been written. Kind of a standard way of doing software architecture. Decomposition of the system into elements and their interactions. But these other two pieces of code seem to be done much more along the lines of the second one. Express the requirements by composing abstractions. This is the way that I best found to express it if I only have 4 words to express it. But there's actually quite a lot more to it. When you do it this way, you end up with a very different kind of structure. Something more like this. There's a layer on the top where just information about your user stories exists. This is cohesive information if you think about it. And there's nothing else goes on here, no implementation, nothing else, just the user stories by instantiating abstractions from a layer below, configuring them and composing them together. The abstractions in the layer below know nothing about each other. They're zero coupled when you do this. And to enable the instances in the user stories to actually communicate, They use what I call, well, they're very abstract interfaces. So they're not interfaces that are particular to any pair of abstractions. They're abstract interfaces. I call them paradigm interfaces because they roughly correspond with what we think of as programming paradigms. Things like just data flows or activity flows. So I'm going to use an experiment we did, and it'll double as an example. So I took this device that I've shown you, and I decided to start again and express the requirements by composing abstractions, just to see what would happen. So this is one user story, or the UI facing part of one user story. I'm just showing you this so that you can relate back the diagram that I did to this. So you can see there's some soft keys on the left. There's a grid showing some data that's obviously binded to some kind of persistent database. There's a menu in here, there's a search box. Okay, so these are the kinds of things. This is one of the simpler user stories. In fact, it's the simplest one. And this is the kind of diagram that I drew to represent it. So the thing on the left was the page, and I first started going, okay, well, I've got some soft keys on there, so I'll draw some lines to represent that there's like UI layout going on. And then the soft keys, all we need to specify on them is labels and where they navigate to, or an action, what they need to do. So I put that sort of thing in. And so far this was very easy. So I carried on. I thought, I wonder if I can do the whole thing this way, all the bindings to the data, all the business logic, even the entity relationships and the schema for the data. And I carried on and did this all, and it all worked out. It was about 2,000 nodes altogether, and I just manually turned into code like this. Each of the boxes that you saw in the diagram was an instance of an abstraction, so it turns into one of the new keywords you see there in bold, and the name of the abstraction. This is fluent programming style, by the way. Everyone familiar with fluent programming style? Well, only a few. Okay, it just means that every method returns to this pointer, so I can just carry on and call another method. And it's in C++, but if you're doing it in Java or something, it would be dots instead of these arrows. The configuration then is just a call to another setter, and all the lines on the diagram just become a call to a wire-to method. So very mechanical, trivial, turning it into the code, even though we did it manually. It could be automated eventually. This is the stats from the completion of this. So the original code in the device was about 200,000 lines. The diagram had about 3,000 instances of abstractions in it. So it only took about 2% of the total code to describe requirements. You know, all the requirements, all the details, but only about 2% of the code. And that was now separated out. And then the other thing I had at the end of this architectural phase was 50 abstractions, none of them knowing anything about each other. 0 coupled abstractions. 6 of the paradigm interfaces that I talked about. The abstractions I just invented as I went along, you know, like the soft key one was an obvious one. It had taken 2 weeks. So this is like iteration 0, the architecture phase. So then I thought, well, that was pretty cool. I now have a complete description of the requirements of this thing that's executable and took me only 2 weeks to do. Could it be that simple that all I have to do now is write the code in these 50 abstractions, which are already 0 coupled with each other, so they're like standalone programs, and the whole thing will work? And I didn't know. So at this stage I'm talking to my co-author, or it turned out to be my co-author, and he was pretty interested in all of this. And he said, well, let's do an experiment and find out if this will work. So we got a student in, and back to the same user story again. We said to the student, well, this user story only uses 12 of the 50 abstractions. So we reckon you could probably write those in 3 months, even though one of them was the most difficult one, binding through to the database. And we set him to task on this. It's actually quite an interesting sub-story about how the student learned how to do this and learned the constraints and the observations about how he saw it all. But in the end, what happened was that we have this comparison here. The original team who wrote the original code for this were 3 people, 4 years, so 12 person years. And the student had written 12 abstractions and got it working in 3 months. So it's not unreasonable to estimate about 1 person year if the student had carried on and finished all 50 abstractions. So I put this difference here down to the fact that the architecture had already split the program up into these 0 coupled pieces. Writing these 50, or these 12 abstractions in this case, was easy for him because they were just standalone programs, each one of them. So what about maintenance? So this is a qualitative graph of what the maintenance should be like. The green one is this abstraction layered architecture. And the reason it would go down is because as your domain matures and you get more of these abstractions written and unit tested and working, the amount of code that you're having to do any particular user story is getting less and less and less. And that compares with a loosely coupled type of architecture, which we usually aim for, which would follow more the orange line. Because of the loose coupling, as the program gets bigger or as time goes on, the effort per user story typically climbs up. And if you're really bad, you'd be following the red line. So I wanted to know for a new feature what it would take. And when we did the original code for this device, and version 1.0 was released, the very first thing the product owner said was, I want this feature called the treatments feature. It was for recording treatments of animals. And it was quite an involved feature, so it took the team a further 3 months to do it. So when I did the diagram, I deliberately ignored this feature, didn't think about it at all because I wanted to know how long would it take to do afterwards using this other method. And so I came back to it later and added it. I needed no further abstractions to do it. It was just some diagram, and it took me 1 hour. So obviously I got to add some acceptance tests to that and so on, but still that's quite a dramatic improvement in the time to implement that particular feature. So back to some theory. This is a module structure view of what this architecture looks like. So everyone familiar with the module structure and the components and connections structure, the difference between these two? Anybody? Oh, okay. Well, this is a design time view. It doesn't capture what was going on inside the abstractions when we were wiring instances together. The user stories go up in that top layer, the application layer, and the abstractions I was talking about in the next layer down, and the programming paradigms in the next layer down. And what we have here is knowledge dependencies only. So you're not allowed any runtime dependencies or compile time dependencies in here. What is a knowledge dependency? It's something that will break your design if it's not there. You can't actually understand your design at all without a knowledge dependency. So, for example, the user story, you cannot understand that code that we had in the user story without knowing about the abstractions in the domain abstractions layer. So this is the main constraint in the architecture. You're only allowed these knowledge dependencies, also called semantic coupling. The abstraction level increases as you go down, so that you've got dependencies on more abstract, more stable, more reusable things as you go down. This is a very different type of layering from what you'd normally see. The layering pattern, so a layering pattern has runtime dependencies in it, typically. A giveaway that this is happening is if you have hardware in the bottom layer of your pattern, or you have data, the database in the bottom, or you have UI in the top layer. So that covers almost all layering patterns that you'll see, and that layering pattern is very common. So those patterns are full of runtime dependencies. So instead in here, all those runtime dependencies have been eliminated. They've gone just into the wiring inside those user stories, completely contained, maybe only 500 lines of code in each one of them. So they have completely disappeared as dependencies. You don't have to manage those ones. But these knowledge dependency ones are actually good. So this is my last slide about the theoretical stuff. The complexity is a constant, and the reason is that all these abstractions that we had are like standalone programs. So if you get your granularity right, and each of them is, say, 500 lines of code, then the complexity in any part of your program will be that of 500 lines of code. No matter how big your program gets, they're all just like separate programs. But what about the knowledge dependencies, you said? The only dependencies that were allowed in this architecture between abstractions. Well, it turns out that the way the brain works with abstractions, a knowledge dependency on abstraction doesn't increase the complexity. So you think about this, think about a square root, an abstraction that the brain already knows. When you hear the word square root, the brain goes, oh yes, I know what that is. A neuron fires off, don't worry about the details. And a square root then just looks like any other line of code, even though it's actually referred to something else, which was very complex. So this is a really, really cool thing that the brain's doing that we've got to make use of in software architecture. If we only use knowledge dependencies on abstractions, then all of our abstractions will appear to the brain as standalone programs. And it turns out that knowledge dependencies alone are enough to get a system working. So this is really cool. Now what else have I missed here? The bottom line, it's not actually novel. There are other systems out there that look exactly like this architectural pattern. MapReduce, for example, has this characteristic, or these constraints, pipes and filters, but all the other ones, especially that layering pattern, are dreadful in this respect. There are a lot of significant advantages of doing it this way. The architecture, the output from that first 2 weeks was directly executable. So one source of truth, that eliminates a whole source of problems that we've even been talking about models and documentation and so on. Your architecture itself was executable. Runtime and compile time dependencies are gone. You don't have to manage them anymore. When we did this, when the student wrote the 12 abstractions, because they're hidden by abstractions and not hidden, the details hidden by abstractions and not hidden by encapsulations, the details didn't come back up and affect the architecture. We didn't have to change the diagram at all. It just completely, the original diagram was working. Okay, so I'm going to leave the rest, but lots of advantages there. So where am I at now? I've got a website about it, so it explains it in greater detail and why it works. It's still a work in progress. We've done the experiment that I've just told you about. I've done 2 pedagogical sized programs, which worked out really nicely. And I haven't had a chance to actually do a whole full project using this yet, but we've been using it on legacy code a lot. It's really nice when you're reading legacy code to know how this code would be structured if it was done properly for these quality attributes. And then you can make really good decisions about how much refactoring to do on it. So in summary, it's a reference architecture that optimizes for complexity, understandability, and modifiability. It tells you how to organize your code. The takeaway thing to remember is express requirements by composition of abstractions. The abstractions are the kingpin, really, that makes the whole thing work. And there's these 12 significant advantages that I alluded to. Complexity is the constant, maintenance effort reduces dramatically, and so on. Okay, thank you. So if you're intrigued, please come and talk to me. I'd love to continue this work with somebody. Thank you very much.
Maybe. Okay, thank you. It works. I think no developer would disagree with what you presented. However, I do disagree on one point, or maybe one thought I had is that maybe you get different results if you don't do the modeling yourself, but let the student, for example, do the initial modeling, because simply you have built the system before, even though in the past you have built the system, so you have already some kind of information about what are the leading abstractions. This can change everything.
Yeah, that's true. I was very familiar with the domain and the requirements, and I'm aware that I had that advantage. Interestingly, when the student was doing it, I would mentor him every day for the first month out of the 3 months. And every day he'd broken the constraints of the architecture, and I would re-explain to him how to do it, how to rewrite the code, and he would agree and rewrite it. And after 1 month, he had got it, this part of the structure. But he was only doing the implementation of these abstractions, which were like standalone programs for him. I mean, their only dependencies were on these abstract interfaces. So the question remains, how long does it take to mentor someone to actually be able to do the model, to go, especially go into a brand new domain, and you don't know what the abstractions are, exactly what you're asking? That's an unknown. And anyone who wants to help me answer that question, I would love to be able to do that.